Hello everyone, welcome back to my online class, and today we are in chapter 6, which is the high level design and optimization. In this chapter we will going to learn on how to design the digital system for a specific purpose or target. Also we will learn on how to optimize the design to improve the performance, such as speed, or how to lower the design cost. That means to produce the smaller design or to reduce the power consumption. And also, we will learn how to constrain the design to meet a certain specification. This is the chapter outline. So we will going to learn on the overview of high-level design, and we will look at the design flow, and we will see how we design the circuit starting from algorithm, and we convert to the RTL design, where we have learned this in chapter 5 already. And now we will learn how to design the digital system based on the algorithm, and we will translate that algorithm to RTL design and of course the digital circuit. And finally we will look at the design optimization. We will optimize the speed, we will optimize the size of the circuit, and also the power consumption, and we will learn how to measure the performance of our design. So yes, in chapter 5 we have been introduced to digital design at the register level, which we call the RTL design. And in this chapter we will design the digital system at the algorithmic level, which is even higher than the register level. So we have looked at this level already in chapter 5, where the algorithmic level is uh, one level higher as compared to the RTL level. And the design will start at the behavioral level, in which the designer described the desired functionality of the proposed system algorithmically, right? And optimization deals with the task of modifying the architecture and data movement produced procedure to meet some particular design requirement. Just like what I said, uh, the speed or performance, and the cost, the size of the circuit, and of course the power consumption. So the impact of modifying the architecture at the algorithm level is actually more has more impact to the performance as compared to the lower level of the design. We will see later how we can do that at the algorithm level to produce a good design entry, design planning before we design the our system later on. So why we have the high level design? Because of the disadvantages of the general purpose processor in some occasion. For example, the architecture of the general purpose processor might not yield the best performance. So what is general purpose processor? General purpose processor is the processor that you do the general processing. I mean, it can do many processing tasks, depending on the program that we write to program the that processor. So for example, the microcontroller is the general purpose processor. The microprocessor that we use today is the general purpose processor as well. So for example, if we look at the general purpose processor, maybe we can have a look at this. So when we see uh, when we talk about the general purpose processor, means that the architecture, the hardware inside that processor it's fixed. Uh, we as a user need to program the microprocessor to uh, to instruct the microprocessor to do a job for us. For example, if we want to add a number, for example, we have, let's for example, we have f. We want to add f equal to a plus b plus c plus d using the general purpose processor. So if you look at the architecture of the general purpose processor, let's for example, we have the general purpose register, right? We have many set of registers. Sometimes we call it register files. And let's say we have two registers in this case, and we have one ALU. And let's for example, this is register A and this is register B, and this ALU can perform many functions. So and the connection is just like this. Maybe we have the multiplexer here, and this is for input register from the input, and this data also can go to B for the output. So to perform this operation, we can use this general purpose processor to do that. But we need to remember that in this general purpose register, in this general purpose processor, we have only one processor, one ALU here. Means that if we have adder, we want to use add operation, so we only have one adder. So for example, we want to do this, means that in the first clock cycle, what we need to do is that we need to put A in register A, and then the next clock cycle, what we need to do is that we need to maybe transfer this A to B, and then we transfer B to register A, and then what we do is we add, so this will actually A plus B. All right, and what we need to do next is that we need to transfer C to A, and then add again, and then transfer D to B, D to A, and then add again. So you right, so you need to do add many times in order to get F or get the result, right, by using the general purpose processor. But if you can design your own circuit, so you can have something like this. You can have many adder. For example, this is your design. So you can have AB, and the output here, you have another adder, and the output here, you have another adder, then you have F, right? So this operation can be performed in one cycle or one clock cycle, right? So by having 3 adders at the same time, so you can produce F already, whereas by using the general purpose processor, the process of adding many numbers, so you need to repeat the operation many times, means that you need to use many clock cycle. So in other words, by using your own architecture, the performance is of course better. You can control the performance, right? So that is mean by this, yeah, the architecture of the general purpose processor might not yield the best performance. Yes, of course, this is not the best performance, right, as compared to the custom design, right? And for number 2, might be underutilized by some application. Okay, for this one, for example, if we use a microprocessor for a very simple application, all right? So the microprocessor is expensive, so there are a lot of circuit inside there. But for example, we want to use that for only to read the input from the sensor and to process a simple data, and then just to control some output. So that means that there are many parts of the processor is not utilized, right? But if we design the circuit that is specifically designed for that specific purpose, then we will uh, we will have uh, fully utilize our resources. Yeah. So this is another one of the drawback of using general purpose processor in some applications. And for number 3, might not have good balance between processor speed and I/O throughput. All right. So the processor is normally is designed to be running at very fast speed. That's why it is expensive. All right. But the I/O throughput, the throughput is means that the number of output or result that your system can produce in one unit time. Yeah. So most of the time the I/O is slower as compared to the microprocessor itself. Yeah. So this is the problem also. Yeah, if you use your microprocessor to for the simple application, right? And number 4, of course, if you use general purpose processor, it's consume more power and area and have a higher cost, just like what I said before. Because the microprocessor, this circuit is big. Yeah, you have many components in there, and most of the time we're not using all the features of the microprocessor. So for a very specific purpose, yeah, so that unused features, although we not use that features, but it's consume power. All right, and of course, yeah, you pay for the higher cost for a small application only. So it's better if you design your own circuit or own system to uh, to 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 do that specific purpose rather than using the general purpose processor. So that is why we learn how to design the our own circuit, our own system for a very specific purpose application. All right. And custom design processor is customized to optimize the execution of particular algorithm for a specific application. All right. So what we will learn is to design the what we call the custom processor. Right. The processor is that is designed just uh, to process or to do a very specific purpose for a very specific application. For example, image processing, digital signal processing, digital filter, for example, right? So we will design that. Uh, we will have the custom design for that, right? And this is also known as what we call a fully dedicated architecture, or in short, is FDA. Yeah. So by doing that, we can optimize for optimal performance, and also the cost trade-off. For example, if we don't want to have a very fast speed, so we can reduce the speed, and when we reduce the speed, we can actually reduce the size of the circuit, and also it will use less power. Remember, if we the speed and the power consumption and all, and the area is don't like each other. Yeah, when you go for high speed, of course you increase the power consumption. All right, so when you reduce the speed, so you will also reduce the size and also reduce the power consumption. So we can have the trade-off for that with the custom design later on. All right, so for example, if our application is not mean for speed, so actually we can reduce the speed so that the uh, the design is smaller and also consume less power, but we can have the same result. Yeah, just uh, have a less uh, speed. So let's look at the design flow. So for the design flow, we have this. Yeah, high level design comprises of two primary tasks. Yeah, the first one is to translate the required behavior of the target design. So we have the specification, and we need to translate that specification into what we call the equivalent algorithmic specification. Yeah, the specification transform to the algorithmic specification, and from that we need to map the algorithm that we have into the fully dedicated architecture here. All right, and from that we can start to design using RTL design methodology. Right, so this is the flow. So from the algorithm, yeah, we have the algorithm, and with that algorithm we can do what is called the cost level restructuring and design identification. So we can modify the algorithm to produce a good hardware representation actually. So we can do here, we can see later on what is this, and from that we will translate this algorithm into the what we call the data flow graph, or in short is DFG, right? So the data flow graph will show the uh, data dependency between the input, the processing unit, and also the output. How the data is connected and is processed and transferred between register into to another register, or one resource to another resources. And from the FG, we will do what we call the scheduling and also allocation. So in this process, we will apply the constraint to the scheduling and also constraint to the allocation. So the scheduling is actually to schedule the process into a cycle. The first cycle, what we want to do, the second cycle, what we want to do, the next, what we want to do, all right, until we get the result. And the allocation is to map the process into the hardware resources. Yeah, to use how many register, all right, to have how many hardware resources, how many adder you need to have, how many multiplier, subtractor, and so on and so forth. All right, so we allocate uh, the uh, the process to the hardware unit. Yeah, and from that, yeah, we can convert this into RTL code, where we have learned this in chapter 5, yeah, from RTL code. From RTL code, of course, we can create the control unit and the data bus unit for our design, right? So let's see this. So this is called an algorithm in digital design, all right? So the algorithm can be in the form of equation like this. Yeah, if a equal to 0, then we do this. Yeah, a b plus c is transferred to a. All right, a multiply e is transferred to d, and so on and so forth. But if a equal to 1, so we do this. So this is called computation block, or in short is CB. All right, and here we can see that line 2, 3, and 4 are not clearly specified in which clock cycle the operation are executed. So we can define actually here whether we want to do this in one clock cycle or do this in a separate clock cycle. All right. So depend on the designer to decide that. Yeah. So that will impact on the size of your design and also the speed. Yeah. And of course the power consumption. All right. When you decide whether you want to execute this in parallel or in sequence, right? So of course they could be executed concurrently at the same clock cycle or in sequence, yeah, depend on the designer. So now let's look at the first flow, this one, the cost level restructuring. What is that? So there are three. The first one is to remove the redundant operation, yeah, or what we call eliminate common sub expression. For example, uh, we can do something like this. So if we have an equation like this, okay, so we can factor a, and we have b plus c. So here we can reduce the size of our circuit already, right? Where we have only one a here and one multiplier here, right? One multiplier and one adder here, all right? Here we have two multiplier because we have two multiplication, right? By factoring, or maybe sometimes we have something like this. Okay, we have two equation, x and y. So when we see this, yeah, at this equation x, so we can actually rearrange this equation. X is actually equal to a plus c plus b, and if we look at this, we can see that this term is the same. All right, means that we can share this operation in one share the resources. Yeah, means that this is one operation only, right? As compared to this one, you need to do this, and do this, and again you need to repeat the operation here. But if you combine this yeah, into one processing unit, then you save the size of your design already. All right, so this is another example of cost restructuring. All right, cost level restructuring. And number two is algebraic transformation can lead to less resources. Uh, less resources utilized. For example, multiply you can replace by shift operation, and of course, for example, you want to multiply by 2. All right, so again, for example, you want to do this. Yeah, for example, you want to do this 5 multiplied by 2. Okay, so actually you can shift to the left. Yeah, shift 5 to the left one time and you can multiply by 2 already. So for example, in the binary, so you have 5 is, right? So 5 multiplied by 2 is 10, right? 10. And let's see here, if you shift this bit to the left one bit, so you can have 1, right? So because 1 is shifted to the left one time, and 1 now is replaced by this 0, and we have this, and you have a new 0 coming in, right? So you have 1 0 0, 1 0 1 0, 1 0 0, 1 0 1 0 is actually 10 in binary, right? So that is how you use shift as compared to multiply. Why? Because multiplication is expensive. All right, we learned already in the previous chapter that to build multiplier is not that easy. You need to have many adders uh, connect together, all right, to build a multiplier. All right, so the multiplier is expensive, whereas to shift the number is very easy. You can use the shift register to do that, or you can have the shifter circuit to do that, right? So this is reduce the cost significantly, all right? And the last one is what we call the tree height reduction. So this tree height reduction is can lead to faster design. Yeah, so for example, we have something like this. Again, if we want to do uh, f equal to a plus b plus c plus d, so in hardware what we do is actually like this, right? Just like the previous example, you have 3 adder in this case, right? So you have AB plus, and you have C, and you have D, did you have F in this case, right? So this we call adder tree, okay? But if at the equation level, if we do this, all right, we group this together, and we have this, and now instead of using this, so we can do something like this. Where we can have AB, and we have C, D, and we have F here. So we can see that this circuit is faster as compared to this one because the propagation delay for this circuit is bigger or larger as compared to this one. Yeah, that's because we can see that the signal this need to travel through this, and through this. Yeah, 3 adders. But this one, yeah, the signal just need to travel from this adder to this adder. So this is of course faster as compared to this one. So the tree height reduction will lead to faster design, yeah, although you may not reduce the size of the circuit, but you can have the faster design as compared to this one, yeah, if you have the adder tree like this, or maybe other processing unit, yeah. So maybe this is the way, a better way to implement the hardware. All right, so that will be this part, yeah, from the algorithm. So we can alter the algorithm so that we can have a better design later on, yeah, based on this method. Right, now look at this. What is DFG? All right, so DFG is a data flow graph. DFG, yeah, an intermediate representation that display data dependencies, and identify the operator used in the algorithm. All right, this is very important statement. Yeah, shows the data dependency. Yeah, how the input, all right, the data input or the output is depend on the input data, right? And identify what is the operator that is used in the algorithm. All right. After the FG is derived, the process called scheduling and allocation are performed. All right, just like this. After this, we do this allocation. Yeah, just like I said, allocation assign operation. No, the scheduling assign operation to clock cycle, and allocation determine the computation resources required to perform the operation. Yeah. Uh, this is the DFG. So we can see that, yeah, this shows the dependencies of Y, right, with the input here A, C, and D, right, where the data is flow this way, right, and the operator that is used, which is the add, yeah, addition, adder, and the multiplier here, right, means that in this case, when we look at this, right, so this is actually, all right, Y equal to A plus C multiplied by C plus D. Okay, so this is A plus C, and this is C plus D, right? And multiply here, we have Y, the output. All right, so we can see that from the equation or algorithm here, yeah, we can create the data dependency or DFG like this. All right, and from this DFG, we need to do the scheduling, all right, where we assign the operation here to the cycle, and also to allocate the computation resources, yeah, to this process. Yeah, so for the scheduling, all right, for the scheduling, we have two type of scheduling, and the first one we call it as soon as possible scheduling, and the second one is the as late as possible scheduling. So this is scheduling, yeah. We can see that the DFG here, we can change this to this where we assign the cycle to the process, to the DFG here, where we can see that here is done in the first cycle, and the next process next at here is done in the next cycle, cycle number 2, and this is cycle number 3, number 4, and number 5 until you get the output here. All right, this is called the as soon as possible scheduling, where we can see that here from the DFG here, because this one is actually not depend on this flow, so and the output for this process is used here. All right, but before that, all right, actually you can do this operation at the first cycle, all right, as soon as possible, right, because this one is not depend on anything. All right, so you can have this operation as soon as possible here at the first clock cycle, all right, cycle number 1. Okay, and also this one, all right, we can have this operation as soon as possible. So here as soon as possible means that in cycle 1, so we have this operation done already here, and when the data and uh, and when we want to use the data, we just read from this. All right, but for as late as possible, we will do the operation, this operation, all right, because we want the data to be available in this cycle number 3. So this one must be done just before cycle number 3, right here. Okay, so we need to make sure that the data is available just before the operation here, right, because this operation we need the data from this operation. So before we do this operation in cycle number 3, we need to make sure that we do the operation. All right, so this is as late as possible, because just before the operation is performed here, we do the operation here, right? Same as this one. All right, instead of perform the operation here or here or here or here, so this one is as late as possible, just before the data is needed here, right? This we call as late as possible. Now from the DFG, right, so we need to do the allocation, where we do what we call the resource binding. All right, so for example, the A, the input, we need to put that A in the register actually. All right, and B also in the register, and C also in the register. All right, in this case, A is stored in register R1, B in R2, and C in R3, right? And when we add, right, when we add the number, these two, A and B, and we will store the result in R1. All right, so this is a resource binding and allocation. All right, we allocate the data into the register. All right, so and also the processing unit here, right? So and again we have this, and we get F, whether F we want to save in the register or send to the output, right? So here we can actually write the RTL code to represent the operation for this process. So for example, at cycle S0, so the RTL operation will be R1 A, right, where A is transferred into R1, R2 B, R3 C, right? And for S1, yeah, is we have R1 is actually R1 plus R2, right? And the last cycle is F is actually R1 plus R3, right? This will be the RTL code for this design, right? Now look at this example 6.1a, right? This is the same algorithm from listing 6.1. So if we have a equal to 0, then we do this, and else we do this. Yeah. So for this computation block, all right, this will be the DFG, where we have a equal to b plus c. We have a here, and here d is actually a multiplied by e. We have d, and m is actually d minus a, so we have m here. All right, so this is the DFG to represent this computation block. This one doesn't need the DFG because it's only a simple operation where we transfer a to m only, so we don't need this for this one, right? And let's look at the second example, 6.1b. Obtain the algorithm corresponding to the DFG in figure below. So this is the DFG. So the algorithm is, of course, we have m equal to a plus c, and n equal to c plus d, and y is m plus n, or we can say that y is actually a plus c multiply by c plus d. So this is not plus, yeah, this is multiply, right? Y is m multiplied by n. Okay, so this is our algorithm. So from DFG we can get the equation back, or from the equation we can get the DFG. Okay, now look at this. So in order to obtain an efficient hardware mapping of the algorithm, data dependencies should not be present. Otherwise, there is a need to include hardware to check for these dependencies. Hence, the algorithm should be in the single assignment form that obeys the following single assignment rules. Right? So, to have a good design, so we need to make sure that we have what we call a single assignment form. So again, what is assignment? So this is assignment. B plus C is assigned to A. Yeah, A multiply E is assigned to D, and so on. So this is assignment. So what is mean by data dependencies? So data dependency is something like this. So for example, if you have A, you have B plus C is assigned to A, and the next statement is D plus E. All right, so we can see that the first statement, the operand here, this is called operand, right? We can see here the operand of the first statement is depend on this one, or this statement is depend on the second statement. All right, so this is not good because we need to make sure that this should be happen first before we can uh, do this. And this is difficult, yeah, because in our design, is executed in a sequence, and we have this first, and this one is actually depend on the second one. So we cannot guarantee that this B is valid before we uh, read A. All right, so this is data dependencies. So to avoid that, so we need to make sure that the assignment that we write must obey these single assignment rules. So what is that? So number one, no two statement may write to a same variables. Means, for example, if you have one variable here, A, so you cannot do this. All right. Means that this is two statement. Yeah. You have two statements here, and these two statements you write to the same variable A. This also write to this, and this one also write to this. Avoid this. And the second one is an operand of one equation cannot be written to by a later equation. So actually this is the example where you see this is the operand of one equation, and another statement you write the write this result, yeah, D plus E into the operand of this operation. So this is cannot be done also. Okay, so that is the rule. And let's see here example 6.2 whether this can be done or cannot be done in writing the assignment. Okay, so at first line, so we have A, B plus C is assigned to A plus D is assigned to B, and so on and so forth. We can see that this number 2 cannot be done because this violates rule number 2, where we can see that here the operand of the first statement, yeah, you write this data to the operand here, so cannot. So this one also the same, violates rule number 2, where you write new data here into the operand of the first statement. So this is not allowed also. This one also violate rule number 2 here, because yeah, you write to this same operand variable here. All right, and here is the operand you write here, and also this is the operand of this, right? And this one you violate rule number 1, because here A we use already for this statement. All right, so this should not be allowed, yeah, for a single assignment form. So we need to change this to this A, right? B plus C we change to A, and A plus D we change to another name. So in this course, this example, instead of B1 B, we use B1, right? So meaning that this statement is written to a new variable here, not B, yeah, but B1. And this one also B1, yeah, is we can use B1 because this is B1 now, and this is C1 instead of C, right? And this is D1 instead of D, right? Because you have D here already, and here this one instead of A, yeah, you change to A1, then you are safe, right? Next is this in high-level design methodology, the behavior of the system system to be designed is specified by algorithm. Yes, we know this. Algorithm can be expressed using equation. So in the previous example, we use equation and also pseudocodes, right? So this one is pseudocode and also the equation. Maybe flowchart or ASM chart. Algorithm based on mathematical equation are typically of specification. Algorithm based on mathematical equation are typical form of specification of signal and image processing system. So for example, you want to design an image processing system or digital processing hardware. So normally the algorithm is in the form of equation. Yeah. So later we will see how we from that equation we want to create the hardware to implement that algorithm or equation, right? So in this example we will continue in the next video.